Let's move on to question 15 and 16, where we are given there are two wires, 1 and 2, and there is a loop of radius a, and these two distances are d each. This is PQ, this is RS, and we are given a particular direction of current here. So the figure shows a circular loop with two parallel lines. The distance from the center is I. The current in the loop is in the counterclockwise direction. So question 15 says when D is approximately equal to A. This basically means when D is equal to A, except these are not touching. When they touch, then continuity might not be violated. Some current going here might go into this wire or something. So just for the sake of that, they have said that it's not touching, but for all practical purposes, we'll just take D is equal to A. Right. It is found that the net magnetic field on the axis of the loop is 0 at a height h above the loop. Right. So we already know what the magnification for a loop is. The formula for that is if we look at it from this direction, if we look at it the side view, then this is the loop we'll see, which has a radius a, and at a height h from this point, the magnetic field due to this loop will be given by mu naught I a squared by 2 times a squared plus h squared to the power 3. But this is a standard result, I won't derive it, and it depends on what the direction of the loop is. If it is such that it's towards the fingers curl towards the right hand like this, then it will go towards this side. Right, it's along the axis, that is the important thing. So mu naught I a square by a square plus h square to the power 3 by 2, we'll just write it more clearly, is the magnetic field due to the loop. This is the B loop. What is the magnetic field due to the wires? Now this question I really like, because one thing we need to do in this is to look at perspectives a lot, and this is the way this would look plus the two wires here if we look at it from this side. What about if we started looking at it from the top? That we need to do in order to look at the magnetic field due to the wires. So from the top, this would just be a wire, right, and this would be the other wire. This is, let's say, point S, and this is point Q, which we are looking at. Here you will have the center along this line, and what you'll have is a point H from here. This is A, this is H. We need the magnetic field here, right, and here. So if both of them have a magnetic field in the same direction, let's say going into the plane, then the magnetic field due to this one will be like this, perpendicular to the line due to S, and due to Q, if it's also going into the plane, will be like this. Now the sum of them will be like this. But we don't want it to be in this direction, we want it to be in the horizontal direction. That means Q and S will have to have currents in the opposite direction. Right. So let's say Q has current going into the plane. So this is the direction of magnetic field for Q. And S has the current coming out of the plane. So the direction for magnetic field from S will be like this. And they will give the resultant here. Right. I'll just try to draw this one again, because A seems to be equal to H, which doesn't need to be true. So we need to draw a figure with a better perspective. So this is S, this is Q. They are not joined. I'm just joining them for the sake of manipulation now, right? But let's say this is H. So if this has a current going into the plane, this has a current coming out of the plane, this will have a magnetic field perpendicular to this line like this. Q and S will have a magnetic field perpendicular to this line like this, and they will have the resultant like this, which needs to be equal to the B of the loop, right? So this is A, this is H. Let's call this angle theta. This is 90 minus theta. So B due to the first one, Bs, is equal to mu naught I by 2 pi S. That is 2 pi A square plus H square to the power 3 by 2. and we take cos of 90 minus theta for this, which is sine theta, to go in this direction. And we double it because this is the same contribution by q. So we double it, and then we can put the value of sine theta. Sine theta is a by root of a square plus h square. Right, so this is just root of 1 by 2. Right. And now here, sine theta can be written as a by root of a square plus h square. So you just get a by a square plus h square. Right. Now these two things have to be equal. Right. So we can just equate them. Mu naught I and mu naught I will cancel. And this 2 will, let's say, cancel with this 2. And what we are left with is, we need to find the relation between h and a. Right. So what we are left with is mu naught I, a has been cancelled, which a is left. So a by a square plus h square to the power 3 by 2 is equal to 2 by pi root of a square plus h square, pi into a square plus h square, no root, sorry. Right, so a square plus h square we can cancel, this will be root of this, means this to the power 1 by 2 is 2 by pi. So we can just say that pi a or pi squared a squared is equal to 4a square plus 4h squared, or h is equal to a times root of, so 4h square will be pi square minus 4. So pi square minus 4 by 4. And if you try to calculate this value, it will come out to be, the pi square is approximately 10. So 10 minus 4 is 6. 6 by 4 is 3 by 2. Root of 1.5 is approximately equal to root 2. So the answer 1.2. 1.2 whole square is 1.44. So it's approximately 1.2a. So 1.2a, and they are going in the opposite direction. So it's either C or D, and the direction has to be PQ and SR. Right? It can't be PQ and RS. It has to be PQ and SR. So the answer is option C. So this is a good question. One of the more difficult questions, not requiring just knowledge, but actually a level of intelligence to be able to calculate these terms directly as well. I like this question. Let's move on to question number 16, which is based on the same concept, based on the same comprehension. So in 16, we have the approximation D is much greater than A, and the loop is rotated about its diameter parallel to 30 degrees. If the current in wires are in opposite directions, the torque at its new position will be. So this is a much simpler problem, because in this we are only talking about between the wires, not at inside or outside the plane. So if they are in the opposite direction, the magnetic field due to them will be 2 times mu naught I by 2 pi d. Right, they'll be in opposite direction, so the magnetic field will add because of them. Right. Now this is the magnetic field. We know the torque is equal to mu cross B. Mu is, now we don't have to worry about anything else because the loop is very small now. So for the loop, the mu will be pi a squared times I into B, that is mu naught I by pi d, into sine theta. And since it's rotated by 30 degrees, this will be sine 30. So which gives me, the pi and pi cancel, a squared mu naught a squared I squared by d, and there's a 2 here because of sine 30. So that gives me the answer as option B. So the answer to question 16 is B.